In this video, we'll talk about incorporating dummy variables that have some sort of ordinal information in our regression analysis. So we're going to work with this data set that you've seen before, which is called Beauty, which is a data set that was constructed to capture the effects of physical attractiveness on wages. So in our data set, we have a ranking of physical attractiveness of each person, a man or a woman, on a scale of 1 to 5, with 5 being strikingly beautiful or handsome, right? So this data set is a subset of the data that was used in Hammermesh and Biddle's article in 1994 that was published in AER. Now, the idea here is if we were to regress, let's say, log of wages on this variable called looks, which takes a value of 1 to 5, moving up on the scale from 1 to 5, the coefficient on looks would capture that. So basically it tells us if looks were to go up by 1, then what is the percentage change in wages, right? So one question you might want to ask is that why should a 1 unit increase the wages by the same amount, right? So the looks variable here is actually an ordinal variable where the order matters, right? 1 to 5 means something. These are not random values, these are ordered. And these are conveying some information. So where you lie on 1 to 5 matters. So what we don't know here is the difference, whether the difference between 5 and 4 is the same as 2 and 1, for instance. So here's the look at your data set, which has information on wages, log wages, and looks, which is this variable that takes values between 1 through 5, right? And so here you can actually look at the range of any variable. But there are some other variables that are constructed that would make more sense. So if we took 3 as the sort of the midpoint, because looks is taking these values, and 3 was average looks, then we can construct, let's say, we can construct below average and above average as 2 dummy variables that take the value of 0 and 1 depending on whether looks are below or above average, right? So if looks takes the value of 4, for instance, then below average would take the value of 0 and above average would take the value of 1 for this person, because 4 is above 3, which was average looks. Okay. Similarly, if somebody had a score of 2 in our data set, then below average would take the value of 1 and above average would take the value of 0. Okay. So in other words, if we were to incorporate, if we wanted to understand the effects of being above average looks, of having above average looks or having below average looks on wages, we could incorporate 2 dummies and leave out the average looks, which is basically taking a value of 1 when looks takes the value of 3. Okay, so let's say if there was a looks takes the value of 3, both of these would be 0, right? So remember, this is going to be our base category, average looks. Now we can almost, we can see when we examine our data set, and you can do this, that very few people are at the extreme values of 1 and 5. Okay, so in such cases, it's useful to combine the variables into such categories below average and above average, right? So here's one way you can capture this. So if you just use the command table on looks, this tells you that what is the distribution of these scores. And this is telling you that only 13 people received a score of 1 and 19 people received a score of 5, right? Everybody else is situated in scores 2, 3, and 4. So we took average as the base group. And here we can also see and also tabulate below average. So this seems, I guess, much better, where if we look at how many people were below average, it's about 155, which is, if you look at it in percentage terms, this is about 12.3% of our sample is below average. And then you can also see the same thing for above average individuals. So 383 people were above average, which is about 30.3% of the people. So we can now regress log wages on not looks, but below average and above average, because these are two categories that we created. It's not categories, but these are dummy variables that we have created based on the categories that we thought. 3 categories, which are below average, average, and above average. So we're leaving out average as the base group or our reference group. And so any coefficient on below average or above average would be giving us the difference between somebody who is below average relative to a person who's average. Similarly, the coefficient on above average would tell us what's the difference between somebody who's above average and somebody whose average looks. Okay, so let's take a look at the coefficients here. So the coefficient on below average is negative 0.208, and this is significant, right? So we can basically say that on average, people who are below average make 20.8% less than people who have average looks. And then we also notice that above average, even though we have a negative coefficient here, this is not significant, right? So we don't really want to interpret that anyway. But let's say we had got some stars here. This coefficient would just mean that people who are above average are paid 4.5% more than people who are average looks, who have average looks. Now, if you control for other factors, including gender and education, which also you might think those are more important for wages, then you would notice that the difference would fall a bit, okay? So it's always good practice to look at all coefficients and to see if the signs and magnitudes make sense, okay? So let's take a look here, for example. So we introduced the same dummies as before, below average and above average, but we also controlled for other variables, experience, education, experience squared, and also gender, right? And notice these are so significant. Again, above average is not, but everything else is. And notice that the coefficient on below average fell. So this can be basically interpreted as, so remember the way our reports it is funny sometimes, but this is equal to, this can be written as 0.01542. That's the coefficient here. So this is basically saying that, I'm sorry, I moved 2 decimals. This should have been since this is 1, I'm going to only move it over. Right, so this is equal to this. And this is basically saying that people who are below average looks make 15.4% less than people who have average looks, ceteris paribus. Okay, and this is less than the 20.8% that we were getting before when we didn't control for other variables. Okay, so remember that if we did not do this analysis and we literally just threw looks, which is taking a value of from 1 through 5 in the regression, then we would always say that better looks always has to have a positive effect. And then we would not be able to tell this type of a story, right? That the difference between average looks and above average looks is really not there. It's not statistically significant. So here's an example. So here we've done the same thing, but now we don't have below average, above average. We have all the other controls, but we've thrown looks into our regression. So if we throw looks into our regression, we get a coefficient that is significant, and this can be interpreted as, right? So this is basically saying as looks goes up by 1, which is to say that if you went up from 1 to 2 or 2 to 3 or 4 to 5, it's all the same. This is just going to be giving you a 5.6% higher salary, ceteris paribus. Okay. We can also look at the standard deviation of looks and try to come up with something like a beta coefficient, for instance, where we can multiply the standard deviation by the coefficient on looks, which is 0.056, and we can say that a 1 standard deviation increase in looks increases the predictive wage by about 3.8%. Okay, so the coefficient on below average, when we are only running this regression for females, so this is how you can do this analysis. If you really wanted to just look into what is going on with females, for instance, and if this is, if you had a data set that had males and females, but you wanted to subset it, you could do it 2 ways. So one, you could take the data set and you can use the pipe operator on it and then use a row function, a row-wise operator called filter, which is a command that just filters out whatever the condition is in the parentheses, right? So here we're saying filter out females equals 1. So, and then store that into beauty females. The other way you could do this is by subsetting your data. So you can say, oh, we'll see that later anyway. So anyway, we created this and now we're just regressing this on a beauty female, right? And of course, I did not need to include females because this is redundant. So you see, notice here that it says NA. But it's basically giving us a below average looks is marginally significant here. And this is just telling us probably this is true because we only are looking at 430 observations. So we don't have a lot of females in the sample, that is to say. Okay, so one shortcoming in the analysis that we have is that we're not really controlling for occupation, right? So if we were looking at, let's say, supermodels, or we were looking at the modeling industry, we would have a pretty good reason to assume that looks plays a role for wages. So, so this is the problem, but then you can take a look at this article that was published in 1998 where they were looking at whether lawyers' salaries or earnings were dependent on looks, for instance. Okay. There are many other examples. One example in your book also talks about what is the effect of, let's say, city credit ratings on municipal bond interest. You can take a look at that. But there are many other types of examples where you would use ordinal information, let's say captured in credit ratings, or let's say if you were asked to rate your happiness in an econometrics class. I know you're at a 5, which is very happy, right? So you can do any type of analysis with ordinal variables. Okay, and this gives very interesting results, and you can create based on ordinal variables, whether your scale is from 1 to 5 or 1 to 10 or 1 to 100. We can do many different types of analysis by creating dummies like we saw in the below average, above average case.